All right, cool. All right, so today we're going to be going over pipes. So just like in the previous lectures, we saw how to use some tool in Bash, some feature in Bash, like redirection or running commands. Now we're going to see how to achieve the feature of pipes, how we send information between processes in our own C code using system calls. So before we begin with the body of today's lecture, we can go over the homework like usual. So first question, what files comprise standard I/O? I think, is this what we did yesterday, or is this is new, right?
Yeah.
Yeah.
I thought it was the old homework, because like the first 3 questions are super similar.
Yeah, I think I had tried to fix that with some of the homeworks. There were more questions actually that were really similar in the past. I've tried to fix that, but some of them might be still pretty similar. Yeah, what is standard I/O would be useful. I guess let that be a hint as to what kind of questions you might see on an exam.
I like the redundancy. It's like a good practice.
That's supposed to be the point. Some people find it annoying, but repetition is what builds knowledge, I think. Okay, so we were on 11. We all know the first one, I think. In, out, error. That should be familiar by now. Write a bash command that uses grep to find lines matching hello from standard in, redirected it from a file called my.in. So how do I pass a pattern to grep? How would I pass the pattern hello to grep? Just hello and then my.in. This would fail because what?
Does hello need to be in quote?
No, it doesn't need to be. If it's the first argument doesn't need to be unless you're trying to escape some kind of special escape character, or you have spaces in the search pattern. Then you want to put it in quotes. Why doesn't a program have to open the standard out file?
It inherits the file descriptors from the process that it was forked from.
Yes. So for us, what is, again in that example we had grep hello. What is bash going to inherit the standard I/O file descriptors from? What program specifically? What? Bash, right? So bash is the one that forks to create the grep process. So grep will inherit standard I/O from bash. What syscall duplicates file descriptors? There is more than one answer. Dup, and then dup2. Yeah, so we saw those last time. Write a snippet of C code that redirects a process's standard out to a file called my.out. So I'm just going to write one line here. If we wanted to use dup2, what would we write to redirect a process's standard out to a file called my.out? I guess I'll write 2 lines. First, I'll create the file. So I'll just say int fd equals, what's this call do we use to open a file? We can use create, yeah. That's like the shorter one. And then we can just say 0644, shortcut for our permissions if we like. What is this equivalent to? What is create equivalent to? O write only, O create, O trunk. So this create system call if I can find it here in the docs. I think I just passed it right here. No. Equivalent to calling open with flags equal to create, O write only, O trunk. So that's all it is. So we create the file descriptor with create. Then how can we redirect our standard out to create, to the file we created? Dup2, what would the first argument be? FD, and what's the last one? Standard out file know. What does standard out file know? What's the actual number? 1. So what is 0? Standard in. Yeah. So what's a way to do this without dup2? dupe, what would we pass the dupe? FD, but what do we have to do in order to ensure that the correct file descriptor is, well, file descriptor 1 is used?
You have to first, I forgot the specific term, but close, STD out, because dupe will just pick the lowest available file descriptor.
Yes, so dupe always picks the lowest available file descriptor by default as the one to use for the duplicate. And to ensure that we redirect the output to standard out, we have to close standard out first because standard out's number 1, so it becomes the lowest available file descriptor if we close it. So that way, the underlying file that FD points to gets a new descriptor with the same number as standard out. This is all like much better to visualize. So I can go back to the slides from yesterday maybe and see if we can see this. Yeah, you can see right, zoom out a little bit. So we saw yesterday, let's see, right here I suppose would be a good one. If we were to close file descriptor 1 first and then duplicate standard out, then 1 would be the lowest available file descriptor. Actually, we'll get right here. You don't need the whole child. 1 would be the lowest, and, well, actually, this isn't a good example either because, there we go, this one's probably the best because we actually have the out.txt file open. So if we close file descriptor 1 first, then, should I just draw this? I think maybe I should just draw this. It's easier for me to just draw this out, actually. So I'll draw, I think I don't need to worry about this being lost. This would be here, here, and then, yeah. Okay, so if we were to call, so we call create here, it creates this third file descriptor for out.txt. We call close. What will that do to the diagram? Yes, so we'll close v1 to here. So we close that file descriptor. And then what is this call to dupe do? Conceptually with this diagram, what would the call to dupe achieve?
It would redirect the arrow from 3 to STD out, or would create a new arrow.
It would create a new arrow. So we would reopen file descriptor 1. And then we would, after it's been reopened, open it as a duplicate of the file descriptor 3 pointing to the same underlying file in the open file table. So now file descriptor 1 refers to out.txt. So why is it that if we write to file descriptor, well, if we were to fork this process, why would the child standard out go to out.txt? Yeah, well, normally what file descriptor does, wait, yeah.
The child inherits the open file descriptors.
Mm-hmm. It inherits the open file descriptors. 1 is open. The child will write to 1, thinking that that's standard out, which it is. But we've changed what standard out points to in the actual open file table to go to out.txt, so the child would write to out.txt instead. Do we want more examples, or should we, yeah?
If nothing ever points to standard out, does it disappear?
Like if nothing were to point to standard out at all? So if all file descriptors, all open file descriptors for a file in this open file table are closed, then the file is removed, I believe, from the open file table. It will still remain in the inode table because that contains all files, whether they're open or not. And remember, we had we showed the inode table here yesterday at the beginning, and then I told us we said we didn't need it, so we skipped over it. It would still be there though. Standard out would still be in this inode table. But I'm not sure if it would even be closed because you might have other processes on your machine that are running that are still referring to standard out, because standard out is system wide, or this open file table is system wide. So if there's at least one other process on your machine, then standard out will not be closed. The other process that has standard out open, it's not going to close on your machine. So we'll see some more implications of that later in this lecture. All right, any other questions? Hopefully it's clear. Okay, so if there's no more questions about how dupe works, then today we're going to talk about pipes. So let me scroll up here, get us ready with our first picture, and I'll close this window. Oops, we can start here. Okay, let me actually pull up my notes so I know what to say. Okay. So pipes, 2 questions. What is a pipe, and how can we use them in Bash? So conceptually, what is a pipe? It's not a redirect.
Passes the output of one command as the input to another.
So it's a way for 2 processes to do what? What? Pass data between them, like you said, yeah. It's a form of inter-process communication. That's the big idea. I guess, small question, what's the other form of inter-process communication that we saw? We've seen a few times. We didn't see it in the last lecture, but I mentioned it before. Not redirection. Not exact. So there's 2 kinds of inter-process communication that we should go over in this course. Pipes and... If I press Control Z, what does that do? Signals, right? Control Z sends the suspend signal or stop signal. So signals and pipes. Pipes is one of the forms of inter-process communication. And how do we use them in Bash? What's like an example of some Bash code that we could use? If I wanted to redirect the output of find user include to grep, how would I do that? The vertical bar, right? Not redirect, sorry. I kind of confused you with that word. So grep, and then we could say .h, find all the .h files and user include. Yeah?
Is there a difference between using single quotes and double quotes?
In this case, no. But the difference between single quotes and double quotes, more broadly, since you ask, is that double quotes let you expand variables inside them. So for me, the $user variable, which you've all been using for the projects, maybe you're not aware of it, that will expand to your username on the current machine you're on. If I were to do this in double quotes, I would get the same result. In single quotes, it would not be expanded. That's the difference between double and single quotes in Bash. Oh, yeah. I mean replace with its contents. So the variable user is my username. So it expands, Bash will expand it before running the command to my username. Yeah. Okay. So let's, I guess, take a look at a pipe. Actually, let me close this window here. So, yeah, a pipe. The plumbing analogies will persist throughout this lecture. Pipes are really a lot like plumbing pipes, honestly. The more you learn more about them, just a way to send information, kind of like how you send water through one end of the pipe to the other. Okay, let's see what's next. All right. So, a pipe is a kind of virtual file. It's not a real file on our machine, not a regular file. But with the write end and the read end, we can write bytes to one end of the file and read bytes from the other end. So since we can write and read bytes to this thing, what abstraction does it satisfy? The file abstraction. I kind of gave it away in the name of the slide, but yeah. So like we saw before, because files are abstractions, we don't need to, there does not need to be like a actual file on our disk and our hard drive that backs up what we're writing or reading our bytes from and to. We can treat it just as an abstraction in such that we can actually write to a virtual file with a pipe, which only exists in RAM temporarily, and it's like any other kind of file, at least for our purposes of interacting with it, reading and writing bytes to and from it. So for instance, if I go down here, if we, let's see, okay. So if we have two commands here, the ones that like I just ran, find, user include, and then grep.h, they're going to start with the 3 open file descriptors that all processes inherit from what? Bash in this case. More generally the parent. In this case it'll be bash. And how can we redirect these file descriptors to point to the write and read ends of the pipe? The pipe, yeah, so that's how we would do it in bash. What's the syscall, I guess, that we would use to perform redirection? Dupe, right? So what we're going to be seeing today is how we can use the dupe syscall to achieve this scenario where the standard out of user include is redirected to the right end of the pipe, and then the standard in of the following command is redirected to the read end of the pipe. And we're going to see the pipe syscall that we can use to create this pipe, and then how we can use the dupe syscalls to actually achieve this redirection here. So I think maybe one question you might be wondering is, why do we even need the pipe? Why can't we just, yeah, I see you're nodding, so I'm glad I anticipated that question. Why can't we just do this and just directly connect standard out to standard in? What's the point of the middleman?
What if the first process still needs standard out?
That's one point. What if the first process need? Well, the standard out's already been redirected to the pipe, so we're going to lose. Oops, we're going to lose that pipe anyway. For some reason, this Control Z is not quite working the way I want it to. Let me reopen this file. Yeah. Okay, so maybe you saw the answer there below. But can anyone think of why? Think about how redirection works under the hood, what we're doing to the open file table and the file descriptor tables for each process. Why should we not simply redirect standard out to standard in? Okay, so you're getting to the correct answer, yeah. So, or maybe you have the correct answer, just not articulated fully. There are files that are already perhaps open, some, well, other processes that are running that still have standard out open and not redirected. So I'll go down here to this table to illustrate this. If we were to simply redirect standard out to standard in, other processes might still be referring to standard in our machine. So we might be interfering with, we're basically changing standard in for every single process. Or not changing it, but we're writing to the standard in that every other process is receiving from. So this would affect all other processes on our machine that are reading from standard in, which we may not want. So to prevent this, we create a pipe to make sure that only these two processes are communicating with each other. So any questions about why we don't just redirect standard out directly to standard in? So again, in this example, we only have grep, but you could imagine maybe we have another program running. Maybe cat, for instance, with no arguments, so it just reads from standard in. And sure, now find's output has been redirected to grep, which is what we want. But now cat, oops, will also be reading from standard in, which has been redirected, well, or is being written to by user include. So we don't really want that. We don't want to interfere with other processes standard in. This is why we use pipes, to make sure that only one process receives a standard out of another. Yeah.
So you're saying the pipe kind of acts like a temporary file that you could read from standard in?
Yes, you can redirect your standard out to and redirect your standard in from. The read end to the write end. So, yeah. Really a pipe is, we're going to get to this, but a pipe is really two files. The read end and the write end are each a separate file, essentially. Where you only read to one and you only write from the other. Or write to one, read from the other. Okay. So this drawing here sort of illustrates how we're actually going to use pipes. Let's see if there's here. Yeah. So basically when we create a pipe, we get two file descriptors back, and we'll be redirecting the right end of one pipe of the pipe. I think maybe it's better if I actually just go to an example now. Because I'm realizing this here refers to the code that I prepared, so I should probably just go straight to the example. I think things will be clearer then. All right, so I have some files here that I prepared for this lecture, and a makefile, of course, for compiling everything. And on the right here, I'm just going to run this makefile run make to compile my code, and then run it on the right like we've been doing in previous lectures. So I'll just open the first example here of how pipes work. All right, so maybe first we should actually look at the pipe syscall itself. So to create a pipe, like everything else we've seen in Linux so far, we use a system call. So in this case, we use the pipe system call. And what pipe does is, if you pass it an integer array of size 2, it will create a unidirectional data channel that can be used for interprocess communication. The array pipefd is used to return two file descriptors referring to the ends of the pipe. Pipefd0 refers to the read end, and pipefd1 refers to the write end. So when we're trying to communicate with the pipe, we always have to write to the right end of the pipe and then read from the read end of the pipe. Now you'll see here on the left, I've created an enum for naming these ends of the pipe because I don't want to have these magic numbers throughout my code, the read end being 0, write end being 1. So you might want to do this in your own projects. Just create like an enum or some macros, some constants. You could say, for instance, define read to 0. And write to 1. This will work as well. Just some way to easily remember for yourself what the read end and write ends of a pipe are. And I think now maybe I should actually show the code here. So in this example here on the left, we're creating this message, hello world. We're getting the length of it, storing in this variable count. And then we're declaring a variable pipefd, and then a result variable. What we're going to do is write, we're going to write the message hello world to the right end of the pipe, and then read from the read end of the pipe, and then print the result back out to standard out. So in this first system call here, we're actually calling the pipe system call, invoking it, and passing it the pipefd array. What this will do is open two new file descriptors, one of which will point to the read end of the pipe, fd0, and then the one at index 1 will point to the right end of the pipe. Here we're going to write directly to the right end of the pipe, and then close the right end of the pipe because we no longer need it. We're done writing to it, we can close it. And then after writing to the pipe, we read from the read end of the pipe, and then can close the read end as well afterward. And then finally we'll write to standard out to see if we receive the message that we were expecting. So if I run this, pipe basic. What do we expect the output to be? What do we think the output might be? So conceptually, and this is why I went back to the code here, because I realize this diagram refers to the code. What we're doing is first writing to the right end of the pipe. This here actually. Control Z is not working again. Interesting. And then closing that descriptor, and then we're writing to the, or reading from the read end of the pipe here. And then printing to standard out. So the message we're sending is hello world to the right end of the pipe and then receiving it from the read end of the pipe. So what do we think the message that we print out should be? Hello world. So if we run this, and there it is. So I guess just to illustrate this another way, put this side by side here so we can really see what's going on. Put the right end here so the diagram becomes a bit easier. Oops. All right, there we go. That's better. Yeah, I put the read end on the left because read is 0, so it made more sense to me, but now looking at the diagram, it would be better if the read end were on the, they were next to the sides of the pipe that they refer to. Okay, so we create the pipe. That's what opens these file descriptors and the pipe in the file table. Conceptually, I'm just illustrating it as this pipe drawing here. And then we write our message to the right end of the pipe. So I'll flip this around here, actually, this arrow. So our message is what? Hello world. So this message is sent to the right end of the pipe. And then here we close the descriptor. So what should we do with this diagram to represent closing the descriptor? We'll just delete the arrow. Yeah. And then we read from the read end of the pipe. So I'll flip this around as well. So we're reading the message back from the read end of the pipe, and then we're closing this descriptor as well. And then printing the message to standard out. And have we changed standard out? Have we redirected standard out at all? No. So that's why when we actually run this program, it actually prints to the terminal still. We have not changed standard out. Yeah.
Is it best practice for me to close the ends of the pipe?
If you're not going to use them anymore, it is.
Okay.
Yeah.
If you plan on using them late, like you can continue to use the pipe later in the code.
Yes. Yes.
I was wondering if it was just a one-time use thing.
No, it's just in general, when you're done using a file descriptor, you should close it. Yeah. Yeah.
What if you don't?
If you don't, then it's just hanging, and that can actually cause, sometimes that's fine, because when a program terminates, open file descriptors will be closed. But in some cases, if you have a child processes that you're trying to communicate with, this can cause problems and actually prevent them from working correctly. We're going to see examples of that later in this lecture, when it can be a big problem not to close an open file descriptor. Yeah. Okay, so I guess the next question would be, how can we use pipes to communicate between a parent and a child process? Let's tie it back to something we've already learned, or reviewed in lecture at least. So how do we, yeah, that's correct. How would we actually make the read end the input of the child and make the write end the output of the parent? What do we do?
You create the pipe first and then you fork.
Yes, create the pipe first and then you fork. You could also, yeah, we'll see more, well, yeah. Also redirection will come into play later, but using dupe and whatnot. But for now, yeah, conceptually that's what's going on. So let's take a look at an example where we do this. Pipe fork.c. Oh, well, I'll just close that. So again, we have this enum for storing the different file descriptors, where the different ends of the pipe are going to be. We declare it here. We create a message, hello from parent. And then here we create a variable for storing the length of the message, and then another variable for storing the result. And what we're going to do is have the parent send this message, hello from the parent, to the right end of the pipe, and have the child read from the read end of the pipe. And just like one of your classmates had said, the first thing we do is create the pipe. So why do we have to create the pipe first? Why can't we create the pipe in the child and in the parent separately?
The child has to be able to access it. If we create it in one or the other, only one would be able to access it.
Yes, so if we were to create the pipe in the child or the parent separately, well, create the pipe in the parent after calling fork, for example, then the parent and the child would have different pipes. They would not have the same pipe. So conceptually, let's go down here to this drawing and hopefully illustrate. We'll actually delete this first. The parent opens the pipe and will have its read and write end referring to these ends of the pipe. Let me draw arrows here to better show this. Keep the arrowheads consistent for now. Kind of ugly here, but oh well, that works. Okay, so the parent has the pipe created, refers to both these ends of the pipe. If we were to call pipe again within the child, what would happen, oops, oh my gosh, this tool is really not cooperating today, I don't know why. Is that the child would actually have its own copy of a different pipe, essentially. It would not be referring to the same pipe. So what we have to do is create the pipe first. I'll just keep undoing. Hopefully the undoing will work here now. No. I don't know why, but my drawing tool here is not being very reliable. Fork and then change the, then with the child having access to the same pipe, we can read from that end of the pipe. So again, creating pipe, calling pipe here, then we can call fork, and then in the child we close the right end of the pipe, so again we're assuming the parent is the one writing, so in the child we immediately close the right end, and then read from the read end of the pipe in the child, and then close this and print a standard out what the child saw, received. Whereas in the parent end of the pipe, in the parent process, we close the read end of the pipe, the parent is only writing, and then write to the right end of the pipe, and then close pipe FD, the right end of the pipe for the parent. So maybe to better illustrate this, what I'll do is here. Before calling fork, the parent has both of these descriptors open, the read and write ends of the pipe. Yeah, question?
What would happen if the child tried to read before the parent
Yeah.
writes?
Okay, good question. So pipes are blocking. Reads to pipes are what's known as blocking. That means that if there's nothing to read from the pipe, then the process will wait until there is something to read from that pipe. hmm So that's why, actually, in this example, we do just that. The child does read without necessarily guaranteeing that the parent has written anything. So let me actually, maybe to illustrate this, I'll run this process here. Gonna make my screen a little bit more clear. Oops. Yeah, there we go. So make pipe fork, and I'll try running this code. We can see it says hello from parent. So the child, the parent I should say, sends the message to the right end of the pipe, and the child reads from it and receives the message and then can print hello from parent. And the child prints to standard out and then flushes the output. We didn't redirect standard out in the child, so the child writing to standard out goes to the terminal like expected. Now if we were to move this call to wait above where we call read here, or before where we actually write to the end of the pipe and close it, actually, I think I might have got this reversed. Maybe I think it's the right end of the pipe that's buffered. That's blocking, actually. So the right end of the pipe blocks until there are reads awaiting. The read end does not block if there are not writes awaiting. In the next example, I'll show this, but I think in this case I've got this maybe backwards. So let's check the man pages and find out. Yeah, so I think this is what's happening. It's still running. Oops. Yeah, sorry, that example wasn't great. But the next one, we'll see how like writes can lead to stop processes. So reads don't, but writes do. Yeah. So, yeah. Okay, so to clarify, the child is reading from the read end of the pipe. The parent is waiting and hasn't actually written anything. This should be pipe fork we're editing right now. Pipe fork, pipe fork. Oh, here we go. So it is working. I think I just forgot my make command. All right, this is much better. This is what I was hoping would happen, and I was worried that didn't happen. Okay, so the child splits off from the parent. Okay, now I can illustrate this, and this should be pretty clear, I think. We create the pipe before calling fork. The child is forked off from the parent. The child inherits all open file descriptors from the parent. So standard out will go to the right end, and the read end will refer to the read end of the pipe still. In the parent process, in this case, we're waiting, and we're not sending anything to the child. So the parent has both of these descriptors open. It sends no messages to these ends of the pipe. Meanwhile, in the child process, the child closes the right end of the pipe, and then the child tries to read from the read end of the pipe. But the parent and the child will wait because it's a blocking operation. It stops the process until it can read something. The parent, meanwhile, is waiting for the child to finish. But the child's not going to be done until it receives something from the right end of the pipe and the right end has been closed. So because the parent never sends anything, it's waiting on the child. It's sort of like a paradox, I guess. The child is waiting on the parent and the parent is waiting on the child, and so nothing ever gets done. And so the process, as you can see, when I run this, it's just hanging. Nothing's happening. So I hope that clarifies things. Sorry for the confusion. I forgot to run that correct make command, so yeah. So So any other questions about this? So in the normal execution, what was supposed to happen, what originally happened, is that if we call wait at the end, then the parent will immediately close the read end of the pipe. Put this to the side here so we can get a better view of what's going on. The parent will close the read end of the pipe. Then it will write a message to the write end of the pipe. It'll write the message hello from parent. And then close the write end of the pipe after writing that message, and then wait for the child to finish. The child is still waiting on that message, which the parent just sent. So now back up in the parent process, the call to read will finish. The child will successfully read that message from the parent. And then the child will close the read end of the pipe and print out the message hello world. It will terminate with exit code 0. The parent will receive that the child is finished, and the program will finish running. So to go through it, maybe, do you want to see it one more time? The illustration? Okay. All right, so from the top, the parent begins by calling pipe here to create a pipe. This opens two file descriptors, pipefd read and pipefd write, and they're pointing to the read and write ends of this pipe, respectively. Then the parent calls fork to create a child process, and what do child processes inherit from their parents? All open file descriptors, right? So we can copy this, put it down here. This will be the child. The child will have the same open file descriptors, so it'll point that are pointing to the same underlying files, the read and write ends of the pipe, after the call to fork. So we're right here now in the code in terms of what's happening. Now, the next two events happen sort of in sequence. The parent and the child run at the same time. But let's go with the child first. Let's just say the child starts running first. The first thing the child will do is close the right end of the pipe and then try to read from the read end of the pipe. So it's going to try and read from this end of the pipe here. But there's nothing that's been sent to the read end of the pipe yet, and the child is trying to read 16 bytes from that pipe. But there's nothing that's even in the pipe, so the child can't do anything. It's just waiting. This is what's called a blocking operation, when the operation causes a process to wait until some criteria is satisfied. So the child is waiting, so now the parent can run. The parent will close the read end of the pipe, because all the parent's going to do is write, so it can close the read end of the pipe immediately. And then it will write the message to the right end of the pipe. So the message hello from parent is being sent to the right end of the pipe here. Then the parent closes the right end of the pipe. So this is going to be closed. And the parent now waits for the child to finish running. So now we go back to the child. The child finishes reading. Well, it's still trying to read from the read end of the pipe, but now there's a message inside the pipe. So the message hello from parent is now in the pipe. We'll make it smaller so you can kind of see how it fits in the pipe. The child can now read this message because it's there inside the read end of the pipe. And then it closes the open file descriptor and then writes the result to standard out. So, oh yeah, question?
So if they run at the same time, so whenever the parent sees something, like whenever it starts writing something down, why does it close why does it close that side of the pipe first before the child goes? So like why does so after it writes, why doesn't the child continue to run now that it's been passed something to read?
why doesn't the child continue to run?
So like if you scroll down in the code,
Yeah,
on the switch statement, so on the default, whenever you, so on that right statement,
yes.
something is written, so now shouldn't the child see that and start running its portion of the code?
It depends on the scheduler, what's going to happen first. So it might be that the parent keeps running, or that the child gets to run immediately. Yeah, it really depends on how the OS schedules this. So we have to write our code such that it doesn't matter what happens first. In this case, it doesn't matter whether the parent closing the right end of the pipe happens before the child reads from the right end of the pipe. Because actually, well, we'll get to this later, but if the child were to try and read from the right end of the pipe without the parent having closed it already, the child will just go back to waiting for more stuff to be written to the right end of the pipe. We'll see an example of that on the next slide, yeah. So if the parent, let's go back here. Okay. So this is just after the call to fork. Just after calling fork. The parent process closes the read end of the pipe because the parent is only writing to the right end of the pipe. It's not going to be reading from it. And then the parent writes the message, hello from parent, to the right end of the pipe. Oops, I got this reversed actually. It's the parent that closes the read end of the pipe, so it should be this one that closes. And then the message, hello from parent, I'll just say, I'll say it. This is the message. It gets sent from the parent to the right end of the pipe. And now let's imagine the child immediately starts running at this point. So the child closes the right end of the pipe, because the child is only reading. And then it tries to read from the read end of the pipe. It can read this message here. Oops. I'll leave this open actually. It can read the message, but I'm not sure if this will happen in this case, but if the right end of the pipe is still open, then the child can expect that there's more information potentially coming from the pipe. So it might hang the process, but in this case it doesn't matter because the child would still be waiting anyway, and the parent is going to close. It would go back to the parent would just close the right end of the pipe. That would signal to the child that the pipe is done having an information written to it, and then the child would just continue executing from there. So, yeah.
Would it be accurate to say that the child only starts reading once the parent closes writing?
The child finishes reading once the parent closes writing, would be the more accurate statement. And I kind of want to go on to the next example now to maybe help. I think that would help clear things up and what's going on here with blocking and whatnot. So any more questions before I do that? Okay, so yeah. All right, so the last example I have here is a combination of pipe, fork, dupe, and exec. So all the things we've seen so far, we're going to combine it all into this file filter.c. And what filter.c is going to do is we're going to implement this functionality that I've been showing throughout the lecture, find, user, include, piping that to grep for .h. So we're going to implement this functionality in a C program. So I'll scroll down here and show what's going to be going on. So the big idea is that the program filter is going to actually call fork twice. It's going to call fork twice, create two children, and then connect the standard out of the first child to the right end of the pipe, and then the standard in of the second child to the read end of the pipe. That way, the two children can be connected. And we're going to see this in general when you have multiple commands whose inputs and outputs you want to connect. The idea is to have the parent call fork multiple times. you go across the hierarchy, not up and down the parent-child process hierarchy. So let me, what I'll do actually is probably delete this, and we'll start from the beginning here. So in the very beginning of this code, we call pipe in the parent. I'll leave the, well, I'll make these blank for now. The parent calls pipe. That's going to create two file descriptors here, pipe read and pipe write. I'll reorder these so it's a bit easier to see. And then we'll call fork to create the first process, the find process. So I'm going to make this blue now. We're calling fork. And fork is going to be a copy of the parent initially, or the forked process will be a copy of the parent. So this is going to be the child filter. And it's going to inherit all the open file descriptors, which means we're going to have the same arrows here. And now in the first child process, we'll assume it just starts running as soon as it's been forked. It doesn't matter, for our example, whether it does or not, because we've synchronized everything to where it shouldn't matter which runs in what order. But we'll assume the first child starts running as soon as we call fork. So the first child is going to call close on the read end of the pipe, because the first child is only writing to the right end of the pipe. It's only going to be, well, yeah, writing to grep. It doesn't have to read anything. And then we call dupe2. So what is dupe2 here going to accomplish?
It's gonna make it the child filter instead of extending it out. It's going to put it into the right end of the pipe.
Yes, exactly. So we're going to, first of all, close standard out, whatever it's first referring to. We don't have the whole file table here, so we can't really illustrate that fully. But we would close standard out, whatever it refers to. And I'm going to actually move standard error over to the side here so it doesn't get in the way. And then we'll reopen standard out to point to the same file descriptor as the right end of the pipe. So in this case, right here. Then we'll close the right end of the pipe because we no longer need it. The child standard out has been successfully redirected to the right end of the pipe. And finally, we'll call exec LP. So what does the L stand for in exec LP? What does it mean? Maybe not what does it stand for, but what does it mean?
The arguments are given as a list, the L means, and the P means that it looks through the directories in your path variable.
Yeah, exactly. So that's why we can specify find here. That's specifying the full path to find because we have access to the path variable. And the L means we can specify find's arguments directly to the call to exec rather than in a variable that is an array. That's what exec V would be for passing the arguments to find as a variable, an array variable. Yeah.
Why do you write find twice?
So that's because by convention on Unix, the very first argument to a program is going to be the name of that program as it was called from the command line. So you always see this duplication of when you make a call to exec. The first argument is going to be the same name of the program, and then the subsequent arguments will be the actual arguments to that program. This is why when we have a C program and you have argv, argv0 is always the name of the program. This is why.
Okay,
Yeah.
so for example, if this was exec VP, it would be like find 0 and then find.
Yes. It would be, or, well, argv would be find user include null, and then we would change this part out for argv.
And you would able to change the find to argv0 as well?
You could just leave it as find. You could change it to argv0. They're both the same thing, right? So you could do argv0. You could also just do find. It doesn't matter. Yeah. Unless I made any typos here, they should actually compile. So make filter. Yeah, they compile. So this works. So any questions before we continue? Yeah.
So a quick question on the do. Does it always close the std out first, or is it just because you put the argument right there inside the do?
It always closes the second file descriptor, the new FD file descriptor. We can see right here in the man pages. If the file descriptor new FD was previously open, it is closed before being reused. So whatever the second argument is, in this case it's standard out, but whatever it was, it would have been closed first before being reopened to point to the same underlying file as the first file descriptor. Yeah. So at this point we call exec. We change the filter function, or filter child, out for ls, or not ls, sorry, find. So that's now what this is. And then, should exec return? No, right? Exec doesn't return, because it should replace the process. So we exit with 1 here, because if exec does return, that should be an error, so we exit with the error code 1. Now meanwhile, or after this, the parent is going to call fork again to create the right-hand side of this pipe up here. So now we're going to create the grep argument, or grep program, I should say, process. So I'll reveal this other end here that I deleted. Maybe I deleted it. There it is, which I had made transparent to hide it. Oh, I guess I deleted most of it. Oh well. Oh, there it is. Okay, so we'll create the second child now. Just copy this over. And what does the child inherit from the parent?
File descriptors.
Yeah, the file descriptors. So we'll have these file descriptors be open initially. And then in this second child, is grep reading from, or is grep going to write anything to the pipe? No, so we can close the right end of the pipe in the child, the second child. And then we call dupe2 again. So here we're redirecting what? Into, what's the input? So we're redirecting what file descriptor to what other file descriptor? So we've written to the right end of the pipe with the first child. So in order to access what the first child has written, what does the second child need to do? Read from the read end. So we're going to connect the standard in to the read end of the pipe. That's the specific file descriptors you'll be accessing here. So we'll connect standard in to the read end of the pipe. And then we can close the read end of the pipe because we've successfully redirected standard in to it already. Close the file descriptor referring to the read end of the pipe. Now here we can call exec LP. So we're going to call exec, this time replacing find with the grep program. So now up here, we've we're actually running this process now in the second child. So to illustrate that, we'll change the name of this process here from filter child to grep.h. Yeah.
This, I can feel this being a stupid question. The arrow pointing from SC into read is describing the order of events, right? It's describing the relationship, not the flow of information.
Just the relationship, yeah.
Okay.
Not necessarily a flow of information. I mean, I can just make it a regular arrow, maybe to.
I just want to make sure I get it, because yeah, it does come from the child to, like, when we go look at the read end of the pipe.
Yeah.
Yeah, the arrow makes sense.
Okay, so this is where we are right now. Any questions before we continue? Okay, so now the next lines of code here, I'm going to make this bigger so we can see everything. The next lines of code will, in the parent, close the read and write ends of the pipe, and then wait for both the children to finish. So wait only waits for one child. We have to call wait twice because we have two children. So conceptually what's going on is we're closing the read end of the pipe first. So we'll close the read end of the pipe, and then we close the write end of the pipe. And now we have this nice pipeline set up where the children can communicate. And the parent will just wait for both children to finish running. So it's going to wait for find to finish running, and then for grep to finish reading find's output. So if we run this, that all being said, what do we think we will see? Yes, exactly. So you have the same result as if we run it on the command line. Because we never redirected grep standard out, so grep standard out is still going to go to the terminal. So now I want to hopefully maybe answer some questions that I think some of you had before. What if we forget to close some file descriptors? Well, let's see if we forget to close the read file descriptor. So we leave this one open in this case. Let's try running this program again. In this case, it still works. Nothing happens. So the parent and the child, the parent, the reason why this works is because the second child, well, the first child actually closes its write end when it's done running. So there's no more information coming into the pipe after the second child is done running. So to be clear, when the first child is done running exec, when exec is all finished, it will close any open file descriptors. So when exec is done running, this file descriptor pointing to the right end of the pipe is closed. There are no more writes pending to the read end of the pipe, so it doesn't matter if the parent and the child are trying to read from it. They're still going to, it's just going to be, they're going to receive the end of file indicator saying there's nothing else to be had from this end of the pipe. They're not going to block. The process is still going to terminate successfully. So leaving an open read is a forgivable offense. It's not something that you can that's going to cause any problems. But on the other hand, let's see what happens if we forget to close the right end of the pipe. So now in this case, we leave the right end of the pipe open and we only close the read end. Now let's see what happens. You can see that it produced the correct output, but now it's hanging. So let's see what's going on here. So the child finishes running just as before, the first child. We can see that it finished running because grep was able to receive the output of find. So we know that the child finished, so its file descriptor should be closed. But the parent still has writes coming to it. And grep is waiting for more input. Grep will filter whatever you give to it until it receives an end of file indicator. But the parent still has the right end of the pipe open. So the file has not been closed yet. With the right end of the pipe still open, the right child is still awaiting input from the parent. So in the next lecture, you will all be assigned the MyShell project. I think it's the next lecture in which we assign it. And you're basically going to be implementing this functionality where you have to support, I think it's just one pipe between two processes. You have to write your own little shell that can take user input and then support a pipe between them. And be aware of this pitfall where if you don't properly close the right end of the pipe in the parent, then the two processes, the second process will just hang. It will stay waiting for more input. Yeah.
What happens if you don't close both?
So if we don't close both, well, what do we think will happen if we don't close both? It's still going to hang, right? Because if we don't close either of them, sure, the read end being open is not a problem, but because we didn't close either of them, the right end is still open. So we're still going to run into the same problem. And I'll just show this just so we can see that I'm not lying. You can see it still hangs. Yeah, so good question. Yeah.
So you mentioned exec automatically close any open file descriptors of that process.
It's just that when a program finishes, its file descriptors are closed. Its opening ones are closed, yeah.
And well, you said there was a important distinction between the underscore exit and the regular exit. What was that?
The distinction is that with underscore exit, the buffers are not flushed. Any buffered output is not flushed. But that's different from closing the file descriptor.
And why would we want to not close the buffer or not flush the buffer in the child process?
It's not so much that we don't want to flush the buffer, it's that we want to use underscore exit. And it just happens to be the underscore exit does not flush the buffer. But why is it we want to use underscore exit and not regular exit? I've mentioned this before.
Regular exit risks closing the parent stuff.
Yes, regular exit will trigger exit handlers, which there are system calls like man at exit, which let you set up functions to be called when a process exits with exit. And remember, a child inherits like a lot of the same stuff from the parent, including exit handlers. So if we were to call regular exit in the child, we might trigger the parent's exit handler twice, which could be bad. So we call underscore exit to avoid triggering that exit handler again. And it just so happens that that involves not flushing buffers. It's not really relevant here because since these processes are replaced with a call to exec, they actually will flush their buffers because they're going to be exiting with the regular exit code because these processes grep and find do exit with the regular exit, so they will flush the buffers. Yeah.
So the exec LP doesn't flush the buffers, but grep does by itself.
Yes, that's yeah. Yeah.
So, back to your program, why does it keep waiting for something to read if you specified it in the exec argument? Like how you wrote grep and then the /.h, shouldn't that be like, I guess, what you're reading from already, or?
This is going to be the pattern we're searching for. But it's not, where are we reading from with grep if we don't give grep a file? Where does grep read from if I don't give grep a file? So if I just type in grep hello, what is grep now reading from? Standard in, right? So I can say hello, bye, hi, hello, and it's reading from standard in. So in this example, if we close read and we don't close write, grep is still waiting to read more from standard in, which has been redirected to the read end of this pipe. But the right end of the pipe is still open. Grep doesn't get the end of file, so it just keeps trying to read. So that's all to say, you can avoid all these headaches, if you just make sure to close the ends of a pipe when you're done using it. Now, you can imagine this is going to get a bit more complex if you want to try and support multiple pipes, because then you have multiple pipelines here between multiple pairs of child processes. And then you have to make sure you close the ends of the pipe at the correct time. But for your project, you only have to implement one pipe. So you don't have to worry about that. Yeah?
For the folks with the parent, would that just be bash in our example?
Yeah. So for our example, if we wanted to do this with bash, exactly, it would just be bash, essentially. So and this is essentially what we're doing. Bash is just forking off and define user include, writing to the right end of the pipe, and then the child is reading from it. I'll maybe make it a little bit clearer. This isn't exactly what the final state of the program looks like, but a bit clearer here. Okay, any questions? Okay, one last thing I want to show, which is not strictly necessary, well, really just something very light to show, just sake of showing that you can do this. You can also communicate with processes using signals, between processes using signals. So this is not going to be in the lecture notes, but the wait syscall down here that we've been using has another variant called wait PID, which lets you wait with obtaining all sorts of information about the child that is running. And again, there's like all these macros you can use to get information about how a process exited. But the big idea is with this syscall, we can do things like this, where I can say make wait, and actually have messages telling me like how the child exited, what signals was sent to it. In this case, we can see that the continue signal is sent to it. All sorts of things like that. I'm not really going to go into too much detail because this isn't really necessary and I don't want to take your time on something that's not required. But if you're curious, just look up the wait PID syscall if you want to get information about a process, how it terminated, why it stopped, or continued with signals. So, how can we send signals to a process? What bash command do we use to send signals to a process?
Control.
That's a button on your keyboard. But what command do we use to send signals to a process? So if I had a really long running command, find / here, and I wanted to kill it, oh, I just gave it away. So I guess the question now is, how can I kill this process? What? I can do what?
It's running in the background, right?
It's running in the foreground. But if I put it in the background, that's a good point. If I put it in the background, now I can't press Control C. That doesn't work.
Pkill find.
Pkill works. So that actually will kill all running instances of find in my machine. It will find them by name and then kill them. You can see it just stopped. What's another way? I don't know if I want to kill all. Sounds like a bad idea. How can I view the process ID of running processes?
Not kill all based off of the specific process name?
Well, kill all will be based off, if I say all, it would probably, well, I'm not really sure. Are you telling me to write just kill all directly like this?
Yeah,
Or-
the name.
Oh, then just the name, like find?
Yeah, if you find it like PS Ox or anything, it's going to kill all.
I think I would need the PID for kill.
But kill all could be based off just the name.
Pkill is the one that goes off of names. I don't know if kill can go off the name alone.
Kills separately, but kill all binary. I'm not sure if it's.
Oh, you mean the kill all program. I don't think we've seen that in this class yet. Yeah, I don't know about that one. We haven't reviewed it in class. So, yeah. Man, kill all. Cool, yeah. Seems like actually, it's probably, if I were to guess, it sounds like a synonym for pkill almost. Apparently it's not, but it's probably the same thing. But cool. So, okay, let's finish running, so I'll just run it again. The other way would be get the process ID of the process it's running. So PSA, and then grep for find. You can see we have one process running here. And then with the regular kill command, you can specify the PID of the process we want to kill, and then kill it that way. Yeah, question?
Doesn't jobs also do PRG?
Yes, jobs will work as well. So I could say jobs, and that would also work. In this case, there's nothing, but if I run it again now, well, I don't think it's going to show anything because this isn't a job in the same terminal. I have a separate terminal window open. But if I were to say Control Z, and then I'm not going to continue it yet because then it would like flush my, dominate all my output. So I'll just say jobs. You can see it stopped right here. It doesn't give me the PID, but it gives me the job ID. So with that, I can actually do things like stop, for instance, or FG to continue the job. I could say FG1, and now that job will continue.
Weirdly, I remember messing with the jobs command, and I was able to go into another terminal and it showed me running process from a different terminal, but I don't know if that's OS specific.
Maybe there is a flag. I don't know. Maybe the terminal you were under was a parent of was a child of another running terminal or something. I don't know. Yeah, I'm not sure. Okay, but that's so much for pipes. I guess we can do attendance. I kind of did it late today, but that'll be the last thing we do then. You have a question?
Yeah, what was the name of the syscall that you said to look up again for like signals?
Wait PID.
Wait, PID?
Let me finish recording here.